Yo-Yo, my classmate, has very good grades, especially in physics. I ask her for help whenever there's anything I don't understand. She is my best friend and really understands me well. Sometimes it seems like she knows exactly what I'm thinking.
Stop dreaming and concentrate on your studies.
Whenever I lose my concentration, she gives me a little push. She says she is just using action and reaction to remind me. She says, this is Newton's third law of motion. For every action, there is a reaction. However, she will go abroad for further studies after the school term, and there will be no one to advise me. Yo-Yo often quips,
Katie, do you know that many laws of physics are hidden in our everyday life?
Of course I do.
Excuse me.
Hey, be careful.
Katie, look! When an object is acted on by external force, a reaction force will be generated. The action and reaction are equal in magnitude and opposite in direction. A ball bounces back because of the reaction force.
Let's imagine if Newton discovered gravity when an apple fell on his head. Could it be possible that he discovered third law of motion while swimming?
Jump right in and find out! To move forward in water, we need to paddle backwards with our hands or kick backwards. This backward force will result in a reaction from the water, which propels the body forward. This becomes even more apparent when reversing. We have to push our feet off hard from the wall of the pool in order to make a turn. Such action generates a reaction force from the wall, which rapidly bounces the body forward.
Is the third law that simple? Since action and reaction are equal in magnitude and opposite in direction, they can cancel each other out, can't they? This sounds problematic.
Let's consider this situation. A horse is pulling a carriage. When it applies force to the vehicle reacts with a force equal in magnitude but opposite in direction. These opposing forces will then offset and cancel each other out, thus resulting in a carriage at the standstill. This is, of course, not true. Action and reaction is a basic concept of physics, which is often misunderstood. Although action and reaction occur at the same time and in opposite directions, they are acting on two different bodies. So they really can't cancel each other out. What Newton's third law really states is, when two bodies apply force to each other, the two forces are equal in magnitude but opposite in direction. Let me elaborate with an example. Two ice skaters are standing face to face, and one of them pushes the other. According to Newton's third law, the person being pushed will react by returning a force equal in magnitude but opposite in direction. As this reaction force is applied on a different body, that is, the person that does the pushing rather than on the same person being pushed, the forces will not cancel each other out. Instead, the two skaters will bounce away from each other.
Regarding the horse-drawn carriage we talked about earlier, its motion is influenced by two forces: the forward propelling force the horse generates, and the friction between the ground and the wheels of the carriage. That is, the force between horse and carriage. and that between ground and carriage. While action and reaction always come in pairs and are equal and opposite, these two forces are not. So as long as the force applied by the horse to the carriage is greater than the force of friction, the carriage will move forward. So how does the horse move forward?
To understand this, we need to understand how we walk. When we walk, we step on the ground with our feet. This is the action we apply to the ground, and the ground reacts by exerting a force that pushes us forward. This reaction is what we call friction, which may be regarded as the cause of the forward movement. The same applies in the case of the horse. What we have considered so far helps explain why it is so difficult to walk on slippery or icy surface. This is because the friction on the surface is very small. As a force, reaction facilitates not only walking but also a variety of movements in our everyday life. For example, a car is capable of moving forward because of the ground's reaction against the force that the wheels exert on it. Likewise, with its propeller, a boat pushes the water backwards, and the reaction force from water drives the boat forward. A jet plane forcefully pushes the air backwards with its powerful engine, and the reaction of the air pushes the jet forward.
However, action and reaction do not necessarily need to be in a contact with each other.
These two magnets operate on the principle of opposites attract and like poles repel. They also illustrate the relationship between action and reaction.
Which then is action and which the reaction? There is no real distinction, as action doesn't have to come before reaction. They occur at the same time and are equal to each other. What is worth mentioning, though, is that they need to be of the same physical nature. How can we explain this?
Take a look at this apple. It is resting steadily on the table, as a result of the balance between gravity and the upward reaction of the table. These two forces are by no means connected to the third law, because they are of different physical nature and they are acting on the same object at the same time. If gravity is the action that the earth exerts on the apple, then gravity's reaction is the force that the apple exerts on the earth. That is, the earth acts on the apple and the apple acts on the earth, and the two do not need to have any physical contact with each other.
But how come we can sense the Earth's gravity on the apple, but not the reaction force of the apple on the Earth?
This is because the apple is too small or insignificant when compared to the Earth. Besides, the contact force exerted by the apple on the table is the action force the apple applies in response to the reaction force of the table.
Have you ever had this experience? When a bus or vehicle suddenly accelerates forward, you feel as though a force is pressing you back in your seat. Or when the vehicle suddenly stops, you feel a force shoving you forward. Either force is called inertial force. However, in reality, inertial force doesn't exist. This is why inertial force is also known as fictitious force. Why are we able to feel it if it doesn't really exist? Imagine I'm standing in a bus. I won't feel any such force when the bus is moving in a straight line at a uniform speed. In other words, no inertial force can be felt with uniform linear motion. Now the bus suddenly accelerates, and I immediately feel a force pushing me back. I therefore have to grab the bus handle for balance. The force pushing me back is the inertial force. What happens is, although the bus accelerates, I don't. I maintain constant speed in accordance with the law of inertia. So when the speed of the bus picks up, I lag behind. As I'm inside the bus, I don't feel the bus moving, but a force pushing me backwards. When the bus suddenly brakes, the situation is reversed. The description, the bus has its own pace and I my own, may be used to describe what happens when the bus decelerates. Though the speed of the bus reduces, I maintain a uniform speed which now becomes faster than the bus, so my body will thrust forward as though I've been pushed. Inertial force is actually derived from the inertia of an object. Regardless whether the bus accelerates or decelerates, I don't readjust but maintain my own normal speed. According to Newton's second law of motion, a force exists only when there is acceleration, so there's really no such thing as inertial force. Inertial force can only be felt or experienced in an accelerated environment, just like when a bus is accelerating.
Everyone must have experienced inertial force before in their daily lives. For example, when riding on a roller coaster, you will feel a large inertial force pushing you back into your seat or jolting you out when it accelerates, decelerates, or brakes suddenly. When the roller coaster goes round a bend, you will feel a huge centrifugal force. It is really a kind of inertial force experienced in an accelerated environment.
What is a centrifugal force, and why is it also an inertial force?
When we spin an umbrella around, the water on its surface will be flung outward. This occurs when centrifugal force is in action.
But why is centrifugal force an inertial or fictitious force?
When an object is circulating in a uniform circular motion, the direction of its motion continuously changes, even though its speed doesn't. This uniform circular motion is in fact an accelerated motion. According to Newton's second law, a force is needed to set off an accelerated motion. A force directed towards the center is required for a uniform circular motion. Similar to what happens to the bus mentioned, when the umbrella is rotated, its water drops will be flung outward along the tangent of the path of the motion as a result of inertia. The water drops on the umbrella seem to be thrust outward by a centrifugal force. Similarly, the rotating swing in amusement parks is a circular motion ride. The centripetal force is essential for setting off a circular motion. People are swung outward by the centrifugal force due to inertia.
Strictly speaking, centrifugal force does not exist. It can only be experienced in an accelerated environment. It should be noted that an inertial force always runs in the opposite direction to the acceleration of the environment.